Hello and welcome to another C++ tutorial. So this time around we are going to be taking a look at maths, and in particular how we can do a lot of common maths things we often need to do in games and do that in C++. So let's dive on in. And so there's a lot of common things that we need to do, and that's going to be really sort of the focus of this. So, okay. First thing is, there is a particular header file we typically want to include. So in this case, what we want is we want CMath. Now for older code, you might see it including the original sort of C1 of math.h, but in this case we want to be including CMath. So, okay, let's look at a couple of standard sort of things. So first one that I think is a useful one is looking at the absolute value. So the idea behind the absolute value is that it takes a number, and whether it is positive or negative, what you get back is always the positive version of that number. So let's test this out. Let's create value 1, and we'll make that minus 1.234. Let's have float value 2. That can be 1.234, like that. Let's have an integer. Whoops, and we'll make that one minus 503. And value 4, we'll just rename that. And this will be 124. So let's just output testing this. So we're going to have our standard C out. Now, one of the things that I haven't done up until now, but you will often see it in C++ code, is it can get annoying to continually have to write this std there like that. So what we can do is we can do a using namespace std, and that will save us needing to do it. Now, something I do recommend is with this, you can actually put this at a range of different sort of scopes. So you can actually put this at a very local scope. So I could actually put it all the way in here if I wanted, and that would work. I generally recommend putting it at the most local scope possible. So I can also put it directly inside main like of this. And I very specifically recommend not ever doing something like this in a header file. The reason being is that whatever scope you put it in, it removes that namespace. So if you have something with the same name in two different namespaces, you can get essentially collisions happening there between them. And this is something where part of the reason namespaces exist and why we don't want to do this in header files is if we take something like games. So in a large game, you might have, you've got the core game engine. That might have a definition for a 3D location in space. Then you might have an audio engine, and it also needs to represent positions, and it might use the exact same variable name or the type name, but it might internally store them differently. So having different namespaces for those allows those to avoid colliding. If you put a using in there, then they can collide, and code can get, depending upon how and where you're working with it, it can be using the wrong one at the wrong time. And that gets very, very messy, and I've seen that cause bugs, and they are very, very difficult to track down at times because they're essentially, they cause essentially the memory to be not corrupted, but not holding the information in the expected way. So it can really be difficult to track down. So usings are fine to have, but the key I recommend is always put them as local as you possibly can. If that means that later on you have to move them out of a function to at the top of the source file, that's okay. Key thing is keeping them as local as possible. And if you're putting them in a header file, you probably shouldn't be. That's usually a bit of a warning sign. If you're putting them in a header file, that something is going wrong if you're doing that. So let's test this out. We've got absolute values. And we can at least nicely now, we just can use directly Enwall like that. So, okay, we'll have value 1, and then we will have that go like this, so we can go and do ABS of value 1, and we'll put Enwall there at the end of that. So I'm going to then chuck in a whole bunch of these for each of the particular ones. And what we should find is the values that are positive won't change, but the values that are negative will change. Comma. That's good. So let's test this out. Let's see how that works. So we'll run it, and we can see in every case we lose the minus sign from it. Positive values are unchanged. So absolute value, really handy. We use that quite a bit. What about rounding? So let's set up another one here that's demonstrating rounding. And what I might do is these values, I am going to bring them up here, just so we can use them in a few more ones. Saves us having to redefine a bunch of things. So, okay, let's test out with this. So one of the common ones is ceiling. So that function is ceil, because sometimes what we want to do is we want to round stuff. We don't want it to round to the nearest. We might want it to always round up. Now, we've provided integers here. It's not immediately showing us an error. Ceiling is generally going to be used, though, with decimal numbers. So let's see what it does. So we can see this goes, because it rounds up, goes to -1, this goes to 2. Nothing really happens with the integers. And so we're going to actually change this to not be bothering with the integer ones, because these are most appropriate for floating point numbers. So ceiling always rounds up. Well, alongside ceiling, unsurprisingly, we also have floor, which, as you might expect, floor is going to round down. So with negative numbers, keep in mind, it's when it means round down, a negative number is going to get rounded. Essentially, the number becomes more negative in that case. So that is something to be aware of. So, okay, that's what ceiling and floor do. We look at other options that we've got with that. Well, do we have just a general round? And the answer is yes. So we can see what that will do. And unsurprisingly, what it's going to do is it's going to round to the nearest value. So ceiling and floor I find really handy, because there are some cases where you do always want it to round up or always want it to round down. Now, obviously with negatives, that can sometimes not work quite the way that you want it to. So one of the things that you can actually do is you can extract the sign out of a value. So if we're wanting to get the sign of something, as in whether it is positive or negative, now there isn't something where you might see in other languages a specific function that you run it and it gives you back indicating a -1 or a 1. However, there is a way that we can do this. So we can do copy sign, and what we are saying here is the left-hand parameter we give it is the floating point number that the sign is being copied to, and the right-hand side is the number that we're copying the sign from. So if value 1 is negative, then this will give us back -1. Otherwise, it will give us back 1. Same thing with value 2. So we're going to test that. So we can see sine is working there. So we don't have the specific, a dedicated function that just you give it a single value, but we can achieve it with a built-in function that's there in CMath with just providing that one additional parameter. So that can be quite handy for that. So there is at least some options there that we can make use of. So okay, we can get absolute values, we can round things, that's pretty handy. Other common thing is going to be doing things like square roots and powers. So square root and power. So we'll test out here square root, and don't need that. And what we'll say is we'll use, let's use one that, it's a fairly obvious thing that we know what the square root of it will be. So we can do square root of 4. And we'll just need to put 0. So, okay, that'll be square root. Well, let's also test power. So let's do the reverse. And we'll take 4. So the power function is usually there as pow. And the arguments are not particularly well named. Generally, the way these work is the first argument is the base number that we're operating on, and the second argument is the power that we're applying to that. So in this case, 4, and then providing 2, should be doing 4 squared. So the only thing we need to make sure we add into this, just to make it so that it is legible, is making sure we've got a bit of a space there, otherwise everything is going to be run together. So we'll run it and we can see. So for the square root, we actually provided the wrong number there, so let's make sure we're providing the right one. So 16, square root of that ends up being 4. 4 squared ends up being 16. If we change that to be 4 cubed, we should get 64, which we can see we do. So, okay. We've got square root and power ones, which are really handy. So that can be useful for a lot of vector maths. It's pretty common with vector math stuff where we might be needing to calculate, squares, square roots, stuff like that of things. So, okay, that's good. What about our trigonometry functions? So trig is a pretty important thing, and in particular in game dev, trigonometry is something that we are often having to work with quite a lot. So one of the big things with doing trig stuff is generally our functions are going to be working in radians. So they won't be working in degrees, but we're often wanting to specify things in degrees because it's a lot more human friendly. After you work with radians for a while, you do get a pretty decent sense of it, but degrees is something that we're generally going to be able to work with a lot easier. So we need to be able to convert them. And to be able to convert them, the easiest thing is if we have a definition somewhere of pi. Technically, the easiest would be if we had an actual function to do the conversion, but we need something that has a definition of pi. Now, there's been a variety of different ways of being able to access this in C++. So there is a range of different ways of being able to access it. And over the course of the language, it's evolved of how we can do this. So what we can now actually do is I will include, so we can include, number. So it's in this numbers header file. And then what we have access to So this is for pi. And what we can say is we can go, we've already brought in the namespace std. To then output this pi constant, what we would access is numbers and pi, but we'll notice we're getting an error here and it actually won't run. And the error is not particularly helpful. So if we take a look in the Solution Explorer and we go to the properties for the project, one of the things we'll see is what the language standard is. Now, this pi constant here didn't exist in the C++ 14 standard. We need to actually switch it to C++ 20. So this is not an unusual thing that you might run into with other compilers as well. Now, as soon as we switch it to that, we can see the error goes away. And if we test for running it, we can see that we get a pi value being output. So just something to watch for, that you can run into that where it's not going to have the particular version. So, okay, we've got pi now available. So let's test out some trigonometry, because that is pretty fundamental for game development. So let's test out firstly sine. So with this, what we want to try is, okay, let's figure out, like, I'm pretty sure I know what this takes as inputs, but let's try with a couple of, particular values. So 0, and we'll do sine of 0. And I need to remember and add in our little spacer here, like that, just so that it doesn't mess up on us. So, okay, we'll try a couple of key values, because I know what the output should be for a bunch of these different ones. So I know 90 degrees, and 180, and let's also chuck in 270. So these are all ones that I know what they should be. And if it's working in degrees, it will be very clear, because this first one will be 0 whether it's in radians or degrees. This second one will be 1 if it's working in degrees, and this one will be 0. So let's test it out. So we can see we need to put in some more endels, but it's definitely not working in degrees, which is what I expected was going to be the case. So that means we need to convert these from degrees to radians. So to convert something from degrees to radians, we multiply it by pi. Now, I don't think there's a constant. Yeah, there isn't one already there for degrees to radians, but we can multiply it by pi and divide it by 180. So I can just put this in for each of these. And now we should see the expected values. 0 gives us 0, 91, 180, that is 1 by 10 to the minus 16. So it's actually very, 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 very close to 0. Technically is 0, but this is where we're getting into floating point error. And then minus 1 has worked as well. So, okay, sine is working. We can reasonably assume then that something like cosine or tangent will also work, but we'll double check just to make sure, because we know what sort of pattern we should see with them. And we'll just put those in. So let's run that. So we see sort of expected values similarly with cos. That looks good. Tangent, again, that's looking about what I would expect with tangent. So, okay. So, okay, we can do sine, cos, and tan. Really handy to be able to do things like our inverse sine, an inverse cos, an inverse tan. And those exist as well. So we won't do as many tests with those. And I will actually shorten the amount of tests we're doing for these. We don't really need to quite do all of that. And for tangent, I might make it that we have a different range of ones that we're testing there. So a sine, so this is for essentially inversing a sine. So going back from a value where we've calculated the sine of an angle and then turning that into, a value, in this case it would be a value in radians. So if I say that the input is 0.5 and then I output the a sine of that, so a sine of 0.5f. Now that will come back to me in radians. So if I want to convert that to degrees, I do the reverse of what I did here. So I would multiply it by 180 and then divide that by numbers pi. Now we can do the similar thing with a cos. So we have a cos, and we also have a tan. So we've set those up there, but the thing we need to fix up is we've put the scaling in the wrong spot. So we just move that out of it, like that. Now we run it. So see, a sine of 0.5 is giving us 30, whereas for a cos it gives us 60 degrees. For a tan, it gives us 26.5 degrees. So that's looking good. Now the other one that we often use is a tan 2, because if we're wanting to resolve where something is in full sort of 360 degrees, so resolve fully across all of the quadrants, we need to be using a tan 2 for that. And we have that function available to us. So what we do is we do an a tan 2, and I'll make it that it is 0.25. So with a tan 2, you provide two values, your y and your x. So I actually swap these around because normally when we're listing coordinates, the convention is x comma y, but a tan 2, the input is y comma x. So we'll run that, and we can see that's correctly given us back a value. So that's good. Our trig functions are working nicely. So we've got a lot of our key maths functions. We also have standard sort of simple ones that we could be doing, and I might throw these in here, of min and max. So a min example would look like this. So for min, let's provide it two inputs, and we'll say that ends up being min 1, 2. And we need to make sure we have the other insertion operator there. We can do the exact same thing with max. If we check those, then we can see min and max are both working there and giving us the values we expect. So those are the, a lot of the common operators that'll, handle sort of a lot of the main things we're needing to do. So the main things to remember is the header file we generally need to include is this one, cmath. If you are wanting to access various mathematical constants, then you want to include numbers. But the thing you might need to do is you might need to, in the properties, set the C++ language standard. So things like pi were only defined from C++ 20 on. So that is something you might need to do. Now, how you do that will vary a little bit if you're using other compilers. So if you're using GCC, then that might be something you're providing instead on the command line. But that's something to be aware of, that you likely will need to change the language standard there. The other stuff to sort of keep in mind is with this, the trigonometry functions, and this is not unusual, but the trigonometry functions, if you are providing an angle, the expectation is that that will be in radians, and if it is generating an angle, it will also be in radians. So you might need to be doing the conversion there yourself. If you're finding you're doing the conversion a lot, you could easily set up a helper function. So we could set up something like this, where we have float deg to rad in degrees, and what we do is we return in degrees divided by 180, and we multiply that by pi. Do the actual multiplication first. So in this case, we would have to do standard numbers pi, like that. Now I could also turn this into something that'll work, in this case it works for floats, but if I wanted it to work for doubles, things like that as well, I could turn this into a template. We could do that like this, and get the version of pi based upon the particular type being passed in. And I could do a similar thing for radians 2 degrees. This ends up being in radians. And we multiply by 180 and divide by that. So, okay, we can test that out and see how that works. So I test that out down here. Conversions. So we would do cout conversions. So there might be a couple of things we need to modify with it. So let's say we're working with 60 degrees. And we could then go and say deg to rad of 60.0f. And we want to put in our extra spacing. Do the same thing then here. Again, like that. And then final thing we'll do is we will do a rad to deg of a degrees to radians. So we might as well run it through both ways. Don't need that extra one there. So, okay, we can test that out. Now, we might have run into a couple of problems. That's okay. So with these, if we're providing the particular type, we actually use pi underscore v like that. And then we can see that runs, and the conversions, 60 goes to around 1 in radians, which goes back to 60 degrees. So while we don't have a nice sort of built-in function often, it's very easy for us to set up versions of those functions, and in this case, a version that'll work regardless of the type of data we're actually working with, which is really handy. So we've got our main functions there. So as I said, Keep in mind you might need to change your project settings. Keep in mind the different header files you might need to include. And keep in mind the fact that, when we're working with our angles and everything, we are having to do conversions there. And that is an important part of it. Well, dive on in and experiment with this. See what kinds of things you can create with this. There's a lot more mathematical functions there in CMath than just the ones I've covered. So take a look at those, see how those different ones work, and experiment, see the kinds of things that you can actually create there. Thanks, folks. Hope you found the video interesting and helpful. If you have, chuck in a like and subscribe. It really helps out. It's really appreciated. If you've got any questions, chuck those in a comment below. If there's other things you'd like to see me cover, you can chuck those in a comment as well. If you're looking for the code for the project, the code is available up on GitHub, and there is a link to that in the description below. And if you're looking for other ways to support the channel, then you can find the link to my Patreon in the description also. But until next time, bye.